Hello students, we are going to start a new chapter today, that is thermal properties of matter. In this chapter, first of all we will understand about what is temperature and what is heat. Then we will see the measurement of temperature, that includes the different temperature scales and different thermometers. Then we will see the ideal gas equation and the absolute temperature. Then we will see the thermal expansion, that is expansion in any material due to the change in temperature. That will include the linear expansion, superficial expansion and volumetric expansion. Then we will see the specific heat capacity, triple point of water. Then we will see the calorimetry, that will include the principle of heat transfer, the specific heat, molar specific heat, latent heat, etc. Then we will see the heat transfer, different ways of heat transfer, that are by conduction, convection and radiation. And at the end we will see the Newton's law of cooling and some previous examples. So let us begin. First, let us understand about temperature and heat. Temperature is the relative measure or indication of hotness or coldness. A hot cooker is said to have high temperature and ice cube is said to have lower temperature. An object at high temperature is said to be hotter than the one at the lower temperature. The SI unit of temperature is Kelvin, but the most used unit is degree Celsius. So basically it is the relative measure of hotness or coldness. The interaction that causes the temperature changes is fundamentally a transfer of energy from one substance to another. Whenever two bodies having different hotness or different temperatures are kept in contact, are kept surrounding each other, then heat will flow, when energy will flow to change their temperature. The energy transfer that takes place solely because of the temperature difference is called heat flow or heat transfer. The SI unit of heat energy transferred is joule, as it is basically a type of energy. Let us understand the main difference between temperature and heat. The temperature depends on the physical state of material and it is a quantitative description of hotness or coldness. In physics, the term heat always refers to energy in transit from one body or system to another because of a temperature difference, and never to the amount of energy contained within a particular system. So by the heat we mean the amount of energy that is transferred and not the amount of energy that is being stored. Now let us discuss various temperature scales and the conversion between various scales. There are basically three temperature scales that we use. One is Celsius, one is Fahrenheit and the Kelvin scale. The relation between Celsius, Fahrenheit and Kelvin is given by Tc minus 0 upon 100 minus 0. Here Tc is the temperature in Celsius scale, is equals to Tf minus 32 upon 212 minus 32. Here Tf is the temperature in Fahrenheit scale, is equals to Tk minus 273 divided by 373 minus 273. Here Tk is the temperature in Kelvin scale. In any other arbitrary scale, the temperature will be given as T minus LFP upon UFP minus LFP. Now, what is LFP and UFP? LFP is the lower fixed point and UFP is the upper fixed point. This LFP is the freezing point of water and this UFP is the boiling point of water. In Celsius scale, the freezing point is 0 degrees Celsius and boiling point is 100 degrees Celsius. In Fahrenheit scale, the freezing point is 32 degree Fahrenheit and the boiling point is 212 degree Fahrenheit. And in the Kelvin scale, the freezing point is 273.15. We take it approximately as 273 and the boiling point is 373.15. We have taken it approximately as 373. So, by using this formula, we can convert the scales. Now, let us see various thermometers. We have classified the thermometers in basically two types, primary thermometers and secondary thermometers. The primary thermometers are comparatively slow and the secondary thermometers are comparatively fast. The types of primary thermometers are constant volume, constant pressure thermometer and compensated air thermometer. The types of secondary thermometers are liquid expansion thermometer, that will include the mercury and alcohol in the glass tube thermometer, the resistance thermometer, the thermoelectric thermometers and the radiation pyrometer. So let us understand them one by one. First, let us understand the liquid expansion thermometer, that is mercury thermometer, which is very commonly used in our day-to-day life. The range of mercury thermometer is minus 38.87 degrees Celsius to 356 degrees Celsius. But the upper limit can be realized about 500 degrees Celsius by filling the top of the tube with nitrogen under pressure, because if we have increased the pressure, then the boiling point of mercury will also be increased. That will become 500 degrees Celsius from 356 degrees Celsius. If we use alcohol, then we can measure the lower temperature as 111 degrees Celsius, and if we use petroleum, then we can measure lower as minus 190 degrees Celsius. So if our job is to measure the lower temperatures, then we can use alcohol or petroleum instead of mercury. The second one is gas thermometer. The gas thermometers are more sensitive than liquid thermometers, as the expansion of gases is more than that of liquids. They are most accurate thermometers and hence to utilized to calibrate all secondary thermometers. All the secondary thermometers are calibrated by using the gas thermometers. But the major disadvantage is that they take almost an hour to record a given temperature, and that's why we use a lot of secondary thermometers. The temperature range is minus 260 degrees Celsius to 1600 degrees Celsius. The gas thermometers are based on ideal gas equation that we will see. And as we know that real gases behave approximately like an ideal gas only at low pressure and high temperature. So, very small amount of gas is filled in the gas thermometer so that pressure remains low. We can find the temperature using gas thermometers by this expression Pt minus P naught divided by P100 minus P naught is equals to T minus 0 divided by 100 minus 0. Here Pt is the pressure at temperature T. P naught is the pressure at 0 degree Celsius and P100 is the pressure at 100 degree Celsius. T will be the temperature in degree Celsius. The resistance thermometers. The platinum resistance thermometer works on a principle of Wheatstone bridge. These thermometers are based on a fact that resistance of metal wire with temperature varies with temperature according to the relation R is equals to R naught into 1 plus alpha T. Here R naught is the resistance at 0 degree Celsius, alpha is the coefficient of temperature coefficient of resistance, and R is the resistance at temperature T. Now how can we measure the temperature using the resistance thermometer? The equation is RT minus R naught divided by R100 minus R naught. RT is the resistance at temperature T. R naught is the resistance at 0 degree Celsius. R100 is the resistance at 100 degree Celsius. So by using this formula, we can find the temperature. Here the temperature T is in degree Celsius scale. These thermometers can measure temperature even from a distance and becomes extremely useful for measuring temperatures where human beings don't go. For example, furnaces, poisonous gases, etc. The temperature range for the resistance thermometer is from minus 182 degrees Celsius up to maximum 1200 degrees Celsius. Now, let us see the next thermoelectric thermometers. It is based on a Seebeck effect. In this thermometer, two distinct metals are joined to form a closed circuit. Let's say there are 2 points A and B. We have taken two distinct metals, let's say iron and copper. They are connected to form a closed junction. This is called thermocouple. Now, one junction is generally kept at 0 degrees Celsius, that is the freezing point, and the other junction is placed on a body whose temperature is to be measured. Let's say T is the temperature is to be measured. Now, due to this temperature difference, there will be a potential difference created between these 2 points and current will start flowing. The current flows is given by AT plus BT square. Here T is the temperature of this body and A and B are constants. We can find the value of current and from that we can find the value of temperature. This kind of thermometers have several advantages. They can easily measure fast changing temperature. Since temperature is in form of electric current, a computer can do the recording of changing temperature over a time interval and it can even be sent through satellites from one place to another. Different parts of our body has different temperature and it can easily make temperature diagrams of our body to be shown on computer. The range of this kind of thermometer is from minus 320 degrees Celsius to 1600 degrees Celsius. The next type of thermometers are the pyrometers. These devices are based on Stephen's law of radiations, which states that the heat radiated by a body is directly proportional to temperature power 4. It measures very high temperatures, that of furnaces or temperature of sun. The next one is the vapor pressure thermometer. It is based on a fact that vapor pressure of a liquid varies uniquely with the temperature. The method consists simply in measuring the vapor pressure of a certain liquid at required temperature. The next one is the magnetic thermometers. Temperatures below 1 Kelvin are measured by magnetic thermometers. It uses the principle of adiabatic demagnetization. It is based on a Curie's law, according to which the magnetic susceptibility of a paramagnetic salt, that is Chi-M, is inversely proportional to the absolute temperature. So, those were the some thermometers and their working. Now, let us see the faulty thermometer and the ideal gas equation. For example, you are given a thermometer whose calibration is faulty. Say for example, it is showing 60 degrees Celsius instead of the value 55 degrees Celsius. Then how will you find the correct value of temperature? The formula we will use is T minus LFP upon UFP minus LFP is equals to T dash minus LFP dash upon UFP dash minus LFP dash. This is for accurate thermometer and this one is for faulty thermometer. T is the temperature of given body which is accurate, which is true. LFP is the lower fixed point in a given scale. For example, it is the 0 degree Celsius in Celsius scale. UFP will be 100 degrees Celsius minus LFP. T dash will be the faulty reading. LFP dash will be the lower fixed point of faulty thermometer and UFP dash will be the upper fixed point of faulty thermometer. Now let us see the ideal gas equation and the absolute temperature. The experiments show that all gases at low densities exhibit same expansion behavior. When temperature is kept constant, the pressure and quantity of gas, that is volume, are related as PV is equals to constant, that is the Boyle's law. When the pressure is held constant, then volume upon temperature is constant, that is the Charles law. If we combine these two relations, that is PV is equals to K and V by T is equals to K dash, where K and K dash both are constant, we can write PV upon T is some other constant, and that is the ideal gas law. The constant we can write here is PV upon T is equals to mu R, where mu is the number of moles of gas, R is the universal gas constant. So we can write PV is equals to mu RT. This is the ideal gas equation. The absolute minimum temperature is equals to minus 273.15 degrees Celsius, and it is also known as the absolute zero. When different types of thermometers are calibrated in ice, water and steam, they agree at 0 degrees Celsius, 100 degrees Celsius, but give slightly different readings in points in between. In gas thermometers, measured temperature agree closely with each other even far from the calibration points. In the one type of gas thermometer called constant volume gas thermometer, the volume of the gas is kept constant and change in pressure of the gas is used to indicate temperature. By changing the thermometer or by placing the thermometer in ice water and water steam baths, the ice point measured to be P0 and P100 respectively. The interval between P100 and P0 is divided into 100 equal intervals. If Pt is the pressure in a bath whose temperature is Tc, then we can write Pt minus P0 upon P100 minus P0 is equals to Tc minus 0 upon 100 minus 0. From this equation, we can find the temperature using the gas thermometers. This equation suggests that pressure in a thermometer varies linearly with the temperature measured. So the pressure versus temperature graph is a straight line as shown in this figure. Now, when we extrapolate these straight lines to zero pressure, the temperature approaches to minus 273.15 degrees Celsius. This limit, which is the same no matter what kind of gas is used. We have drawn the graph for different gases, but for zero pressure, we have the temperature of minus 273.15 degrees Celsius irrespective of type of gas. This temperature is called absolute zero temperature. A temperature scale based on this zero is called absolute temperature scale or Kelvin scale. So we can see that minus 273.15 degrees Celsius is equals to 0 Kelvin. Now let us see some examples based on the temperature scales. In this example, what is the temperature at which Celsius and Fahrenheit scale give the same temperature value? The conversion between Celsius and Fahrenheit is given by Tc minus 0 upon 100 minus 0 is equals to Tf minus 32 upon 212 minus 32. It is given that they both have same temperature in Celsius and Fahrenheit. So let's say Tc is equals to Tf is equals to X. So X upon 100 is equals to X minus 32 upon 180. The 0 will get cancelled out. So 18x is equals to 10x minus 320. So 8x is equals to minus 320. So x will be equal to minus 320 upon 8. So x will be equal to minus 40. So at minus 40 degrees Celsius, the Fahrenheit reading is also minus 40 degree Fahrenheit. In this example, suppose that on a temperature scale X, water boils at minus 60 degree X and freezes at minus 180 degree X, 180.5 degree X. What would be the temperature of 350 Kelvin on that scale? For the unknown scale X, we can write X minus the lower fixed point, that is 180.5, divided by upper fixed point minus 60 minus of minus 180.5 is equals to, we want to find the value that is in Kelvin. So 350 minus 273.15 divided by 373.15 minus 273.15. So X plus 180.5 divided by 120.5 is equals to 76.85 divided by 100. Simplify this for the value of X. We will get X is equals to minus 87.9 degree. So we can write 350 Kelvin is equals to minus 87.9 degree X. In this example, the readings of bath on Celsius and Fahrenheit thermometers are in the ratio 2:5. We want to find the temperature of the bath. The Celsius and Fahrenheit scale are related as Tc upon 100 is equals to Tf minus 32 divided by 180. Tc is to Tf is given 2:5. So we can write Tc is equals to 2x and Tf is equals to 5x. So 2x upon 100 is equals to 5x minus 32 divided by 180. Simplifying this, we will get x is equals to 160 by 7. So the temperature of the bath in the Celsius scale will be 2x, that is equals to 320 by 7, that is approximately equal to 45.7 degrees Celsius. In this example, a uniform thermometer scale is at steady state with its 0 centimeter mark at 20 degrees Celsius and 100 centimeter mark at 100 degrees Celsius. We want to find the temperature at 60 centimeter mark. T minus 20 degree upon 100 minus 20 is equals to L minus 0 upon 100 minus 0. Here given the value of L is 60. So T minus 20 divided by 80 is equals to 60 divided by 100. So T minus 20 is equals to 48. So T will be equal to 68 degree Celsius. So at the length of 60 centimeter, the reading would be 68 degree Celsius. Now let us understand the thermal expansion. Most materials expand when the temperature increases. For example, rising temperature of decks make the liquid expand in the tube of thermometer. The decks of bridges need special joints to support and to allow for expansion. A completely filled and tightly kept bottle of water cracks when it is heated, and we can loosen a metal jar lid by running hot water over it. This all are the examples of thermal expansions. Basically, there are three types of expansion: the linear expansion, that is change in length; the aerial expansion, that is change in area; and the volumetric expansion, that is change in volume, all due to the change in temperature. So let us see them one by one. First, the linear expansion. Suppose a rod of some material has length L0 at some initial temperature T0. When temperature changes by delta T, the length changes by delta L. Experiment shows that if delta T is not too large, let's say it is less than 100 degrees Celsius, then delta L is directly proportional to delta T. If two rods are made of same material, have same temperature changes, but one is twice as long as the other, then the change in its length is also twice. Therefore, delta L must also be proportional to L0. Introducing a proportionality constant, we can write delta L is equals to alpha L0 into delta T. Here alpha is the proportionality constant. It is called the coefficient of linear expansion. The SI unit of alpha is Kelvin inverse. This direct proportionality equation is not exact. It is approximately correct for sufficiently small temperatures. For given material, alpha varies somewhat with the initial temperature T0 and the size of the temperature interval. But here we will ignore this compilation. We will always take the average value of alphas and we will take them as a constant. Now let us see the aerial expansion or area expansion. It is also called the superficial expansion. Experiment shows that if delta T is not too large, again it is less than 100 degrees Celsius, then increase in area, that is delta A, is directly proportional to A0 delta T. Here the proportionality constant is beta. Beta is the coefficient of area expansion. SI unit is again Kelvin inverse. For small changes, we can write the relation between coefficient of aerial expansion and coefficient of linear expansion as beta is equals to 2 alpha. Now the volume expansion. Increasing temperature also causes the increase in volume for both solid and liquid materials. Again, for low value of delta T, that is less than 100 degrees Celsius, the increase in volume is directly proportional to the V0 and delta T. Here the proportionality constant is gamma. The gamma is called coefficient of volume expansion. Again, the SI unit will be Kelvin inverse. The approximated relation between the coefficient of volume expansion and coefficient of linear expansion are gamma is equals to 3 alpha. This is approximated relation for small temperature changes only. Let us understand some important points about alpha, beta and gamma, that are coefficient of linear expansion, coefficient of superficial expansion and coefficient of volume expansion. These three coefficients are not constant for given solid. Their values depends on the temperature range. The values of alpha, beta and gamma also depend on the unit of temperature. The alpha, beta or gamma in the temperature scale degree Celsius inverse are the 9/5 times the alpha, beta, gamma value and per degree Fahrenheit, but it will be same for per degree Celsius and per degree Kelvin. The value of alpha, beta and gamma are independent of unit of length, area and volume. For isotropic solids, gamma, the volumetric expansion, is not 3 times alpha, it is alpha x plus alpha y plus alpha z. This is for anisotropic materials or solids. Here alpha x, alpha y and alpha z represent the mean coefficient of linear expansion along 3 mutually perpendicular directions. Now let us see the expansion of cavity. Thermal expansion of an isotropic object may be imagined as a photographic enlargement. The way we zoom the photo, we can understand it by that. So if they're imagined as a photographic enlargement, there is a hole in a plate. For example, this is a plate and there is a hole. We can say it is a cavity. The area of hole will increase when body expands on heating. This is at temperature T and this is at temperature T plus delta T. Just as if the hole or wall cavity were a solid for the same material, the expansion of area of body will be independent of shape and size of a hole. If two spheres, one being solid and the other hollow, are made of same material having same radius at particular temperature, if they are heated to the same temperature, their radius will be same. So the expansion of both solid and hollow sphere will be same for same temperature change. Now, let us see some example based on the expansions. In this example, a surveyor uses a steel measuring tape that is exactly 50 meter long at 20 degrees Celsius. What is the length of the tape on a hot summer day when the temperature is 35 degrees Celsius? Given coefficient of linear expansion for steel is 1.2 into 10 power minus 5 Kelvin inverse. The delta L will be alpha L naught delta T. Here alpha is 1.2 into 10 power minus 5. L naught is given 50 into delta T is 35 minus 20. 1.2 into 10 power minus 5 into 50 into this will be 15. Simplify this, we will get delta L is equals to 0.009 meter. So at temperature 35 degrees Celsius, the reading will be 50 plus 0.009 meter, that will be equal to 50.009 meter. In this example, a glass flask with volume 200 centimeter cube is filled to the brim with mercury at 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? Given coefficient of linear expansion for the glass is 0.4 into 10 power minus 5 Kelvin and the coefficient of volume expansion of mercury is 18 into 10 power minus 5 Kelvin inverse. Here the increase in the volume of the glass flask, that is delta V, is equals to gamma glass into V naught delta T. Gamma glass can be written as 3 times alpha glass into V naught into delta T. V naught is 200 centimeter cube and the delta T is, initially it was 20, then we have raised to 100, so 80 degrees Celsius. Simplify this, we will get answer 0.19 centimeter cube. Now change in volume of mercury is equals to gamma mercury into V naught delta T. That will be equal to 18 into 10 power minus 5 into V naught 200 centimeter cube because the glass flask is completely filled into delta T, that is 80 degrees Celsius. So we will get the answer, that is 2.9 centimeter cube. Here the volume of glass flask is also increased and volume of mercury is also increased. So the volume that overflows will be equal to 2.9 minus 0.19 centimeter cube. That will give us the answer 2.7 centimeter cube. So this much amount of mercury will overflow. Now let us see how density changes with change in temperature. The density is defined as mass per unit volume. Since the volume of given mass of substance changes with temperature and mass remains constant, the density undergoes a change with temperature. Consider a solid body of mass m which has volume V1 and density ρ1 at temperature T1, and it has volume V2 and density ρ2 at temperature T2. Here clearly the mass will be constant, so we can write mass is equals to density into volume, so we can write ρ1 V1 is equals to ρ2 V2. But this V2 can be written as V1 into 1 plus gamma delta T. Here gamma is the coefficient of volume expansion. That will be equal to ρ1 V1. This rho V1 will get cancelled out, so we can write ρ2 is equals to ρ1 divided by 1 plus gamma delta T. ρ2 will be ρ1 into 1 plus gamma delta T whole power minus 1. Here we know that gamma is very small. It is very less than 1. So we can use the binomial expansion According to binomial expansion, 1 plus x whole power n is equals to 1 plus nx, given x is very less than 1. This condition is satisfied here, so we can write ρ2 is equals to ρ1 into 1, this will be minus gamma delta T. So this will be the new density. Now let us understand the working of bimetallic strip, that is based on the thermal expansion. The bimetallic strip, as the name suggests, consists of two strips of equal length but of different materials. They are riveted together, keeping one over the other. For example, here we have taken one strip of iron and one strip of copper. Now, when such bimetallic strip is heated, it bends with metal of greater alpha on the outer side, that is on convex side. Here, the alpha for copper is greater than alpha for iron. So, when the temperature is increased, given theta 2 is greater than theta 1, the expansion in the copper will be more than the expansion in iron. So, the material having greater alpha will bend on the outer side, that is on the convex side. They are mostly used in the thermostat or auto-cut-in electric heating circuits. For example, in the iron press, when we set temperature for given iron while we press the clothes, once the temperature is reached, then this material will bend in particular direction, and it will, due to bending, it will lose connection with the circuit. So after that the heating will stop. Now again this will start contracting, or this will again start decreasing the temperature. So again it will come to same position. So in this kind of automatic temperature changing, this bimetallic strips are used. Now let us see what will happen when we measure any length using the metallic scale at different temperatures. If a scale, say of steel, gives correct reading at temperature theta naught. Then at temperature theta, that is more than theta naught, due to linear expansion of scale, reading will be lesser than the true value. Also, if the measured object is also expands on heating, then the true value can be written as measured value into 1 plus alpha s into theta minus theta naught. This alpha s is of scale divided by 1 plus alpha object into theta minus theta naught. If the given object is of wood, then alpha object will be 0. Now, let us see the effect of linear expansion on the pendulum clocks. Suppose a pendulum clock gives proper time at temperature theta, and length of this pendulum at this temperature is L. If temperature is increased to theta dash, then due to linear expansion, the length of pendulum changes and hence the time period will change. So let's say new length is L dash and new time period is T dash. The time period for a pendulum is given by 2 pi under root L by G. The time period T dash at temperature theta dash can be given as 2 pi under root L dash upon G. The L dash, that is the length at temperature theta dash, can be given as under root L into 1 plus alpha delta theta divided by G. Take the ratio of T and T dash. We can write T dash upon T is equals to under root 1 plus alpha delta theta. So, T dash upon T will be equal to 1 plus alpha delta theta whole power 1 by 2. For small temperature changes, we can use binomial expansion. So, it can be written as 1 plus 1 by 2 alpha delta theta. So, T dash by T minus 1 is equals to half alpha delta theta. So, T dash minus T upon T is equals to half alpha delta theta. Here, it is the fractional change T dash minus T upon T. This is the change in time. Let's say this is delta T. Can be written as T into half alpha delta theta. The clock will lose time if theta dash is greater than theta, and it will gain time if theta dash is less than theta. The gain or loss in time is independent of time period t and depends only on time period small t. Since alpha for invar is very small, as mostly pendulums are made of invar to show the correct time in all the seasons. Now let us see the effect of temperature change on the buoyancy. The thrust depends on volume V. The upthrust on volume V of a body on a liquid of density rho is given by, let's say upthrust is B, that will be equal to volume of body into density of liquid into G. Now, with rising temperature by delta theta degrees Celsius, due to expansion, volume of body will increase and density of liquid will decrease. So, change in volume or the new volume is given by V dash is equals to V into 1 plus alpha body into delta theta, and the new density rho dash will be given by rho into 1 minus alpha liquid into delta theta. So B dash will be given as V dash into rho dash into G. So taking the ratio, B dash upon B will be equal to V dash will be VB into 1 plus delta theta, rho dash will be rho into 1 minus rho L delta theta into G divided by VB rho L into G. This will get cancelled out. So B dash upon B will be equal to 1 plus gamma B delta theta into 1 minus gamma L delta theta. From this we can find the new force of buoyancy. Now, as gamma S is less than gamma liquid, if gamma of solid is less than gamma of liquid, then B dash will be less than B. So new upthrust will be less than the previous upthrust. And if gamma S is greater than gamma liquid, then B dash will be greater than B. Now let us see example based on what we have learned. A seconds pendulum clock has a steel wire. The clock shows correct time at 25 degrees Celsius. The meaning of seconds pendulum means the time period is 1 second. How much time does the clock lose or gain in 1 week when the temperature is increased to 35 degrees Celsius? Given alpha steel is 1.2 into 10 power minus 5 degrees Celsius. The fractional change in temperature, just we have seen, it is given by delta T by T is equals to half alpha delta theta. We want to find delta T is equals to half alpha delta theta into capital T. So delta T will be half, alpha is given 1.2 into 10 power minus 5, delta theta will be 35 minus 25, that will be equal to 10 degrees Celsius, and T, we want to find the time lost or gain in 1 week. So time in 1 week will be, that will be 7 days into 24 hours into 3600 seconds. Solve this, we will get delta T is equals to 36.28 second. Your delta T is positive, that means the time is lost. In this example, the apparent coefficient of expansion of a liquid when heated in brass vessel is X. When heated in tin vessel is Y. Alpha is the coefficient of linear expansion of brass. We want to find the linear expansion of tin. Here, the apparent expansion means due to the rising temperature, the volume of container will also increase and the volume of liquid will also increase. So the apparent expansion means the volume of liquid increased minus the volume of container increased. Here, the coefficient of liquid is equals to apparent expansion plus expansion of vessel. So, coefficient of liquid let's say it is small x, that is equals to x plus 3 alpha brass. It is x is equals to y plus 3 alpha tin. So we can write x plus 3 alpha brass is equals to y plus 3 alpha tin. We want to find the coefficient of linear expansion of tin. So 3 alpha tin is equals to 3 alpha brass minus y plus x. So alpha tin will be equal to 3 alpha brass plus x minus y whole divided by 3. So this will be our answer. In the next example, the coefficient of volume expansion of glycerine is 49 into 10 power minus 5 Kelvin inverse. We want to find the fractional change in density for 30-degree rise in the temperature. The new density ρ2 is given by ρ1 into 1 minus gamma delta T. So ρ2 will be equal to ρ1 minus ρ1 gamma delta T. So ρ2 minus ρ1 upon ρ1 is equals to minus of gamma delta T. This will be the fractional change. So put the value. Gamma is given 49 into 10 power minus 5 and per degree Celsius the temperature change is given 30 degrees Celsius. So delta T will be 30. Simplify this. We will get the answer 1.47 into 10 power minus 2. This will be the fractional change in the density. The next example, a steel tape is calibrated at 20 degrees Celsius on a cold day when the temperature is minus 15 degrees Celsius. Find the percentage error in the tape. Given alpha steel is equals to 1.2 into 10 power minus 5 per degree Celsius. It was designed at 20 degrees Celsius and we want to find the error at minus 15 degrees Celsius. The percentage error is delta L by L into 100. the delta L is given as L alpha delta T divided by L into 100. This L will get cancelled out. So alpha is 1.2 into 10 power minus 5 into delta T will be minus 15 minus 20, that will be minus 35 into 100. Simplify this, we will get the answer minus of 0.042%. In the next example, the coefficient of linear expansion of vessel completely filled with mercury is 1 into 10 power minus 5 per degree Celsius. This is for vessel. If there is no overflow of Hg, then what is the coefficient of cubical expansion of Hg? Here there is no overflow, that means the gamma of Hg should be less than or equal to gamma of the vessel. So gamma of Hg should be less than or equals to 3 times alpha of vessel, because we are given the value of linear expansion. So gamma of Hg should be less than or equal to 3 into 10 power minus 5 per degree Celsius. In this example, the coefficient of linear expansion of a crystalline substance in one direction is 2 into 10 power minus 4 per degree Celsius, and in every direction perpendicular to it is 3 into 10 power minus 4 per degree Celsius. We want to find the coefficient of cubical expansion. Here, as it is the crystalline substance, the coefficient of cubical expansion is given by alpha x plus alpha y plus alpha z. Let's say alpha x is 2 into 10 power minus 4. Then alpha y and alpha z will be 3 into 10 power minus 4 plus 3 into 10 power minus 4. So gamma will be equal to 8 into 10 power minus 4 per degree Celsius. Now, let us understand the thermal stress. If we clamp the ends of a rod rigidly to prevent its expansion or contraction, and then change the temperature, the tensile or compressive stress is developed. This stress is called thermal stress. The rod would like to expand or contract, but the clamps will not allow it. The resulting stress may become large enough to strain the rod irreversibly or even break it. To calculate the thermal stress in a clamped rod, we have to find how much the rod would expand or contract if not held rigidly, and then find the stress needed to compress it back to its original length. Suppose a rod with length L0 and cross-sectional area A is held at a constant length while the temperature is reduced negative. Temperature is reduced, that means delta T will be negative, causing a tensile stress. The fractional change in length if the rod were free to contract would be delta L upon L0 will be equal to alpha delta T when it is free to contract. Here both delta L and delta T are negative, so we have not given the sign. The tension must increase by an amount F that is just enough to produce an equal and opposite fractional change, that is delta L by L naught, from the due to this supports. Now, Young's modulus for given material can be written as F by A upon delta L upon L naught. So, delta L upon L naught will be equal to F upon A Y. If the length has to be constant, the total fractional change should be 0. So, we can write that F upon AY plus alpha delta T is equals to 0. So, F upon AY is equals to minus alpha delta T. But delta T is negative, so simply F upon AY will be equal to alpha delta T. Now, delta T will be positive. So, the thermal stress F by A is equals to Y alpha delta T. This is the thermal stress produced in the rod. Now, if there are temperature differences within a body, a non-uniform expansion or contraction will result and the thermal stresses can be induced. We can break a glass bowl by pouring hot water into it. The thermal stress between hot and cold parts of the bowl exceeds the breaking stress of the thermal glass, causing the cracks. The same phenomenon make ice cubes crack when they are dropped in warm water. Now, let us see some example based on the thermal stress. An aluminium cylinder 10 cm long with area of cross section 20 cm square is to be used as spacer between two steel walls. There are two steel walls and the rod is used as a spacer. That means this rod has to maintain the space between these two walls. When it warms to 22.3 degrees Celsius, we want to calculate stress. Given at 17.2 degrees Celsius, it just slips between the walls. That means at 17.2 degrees Celsius, it can just fit between two walls. Given Y for aluminum 7 into 10 power 10 Pascal and alpha for aluminum 2.4 into 10 power minus 5 Kelvin inverse. The delta T will be 22.3 minus 17.2. That will be equal to 5.1 Kelvin. The thermal stress F by A is given by Y alpha delta T. Y is 0.7 into 10 power 11 Pascal. The temperature change is 5.1 Kelvin. Simplify this, we will get the answer 8.6 into 10 power 6 Pascal. In this example, two uniform rods AB and BC have Young's modulus given 1.2 into 10 power 11 Pascal and 1.5 into 10 power 11 Pascal. The alpha for AB is 1.5 into 10 power minus 5 per degree Celsius. We want to find the value of alpha BC, for which there is no shift in junction at any temperature. The junction B is not going to shift from this point. Now for no shift, the alpha L delta theta will be equal to FL upon AY. So we can write alpha is inversely proportional to 1 upon Y. So alpha 1 or alpha AB upon alpha BC is equals to YBC upon YAB. So alpha BC is equals to alpha AB into YAB divided by YBC. Put the values. Alpha AB is 1.5 into 10 power minus 5. YAB is 1.2 into 10 power 11 divided by YBC is 1.5 into 10 power 11. So we will get alpha BC is equals to 1.2 into 10 power minus 5 per degree Celsius. In this example, a uniform copper rod of length 50 cm and diameter 3 mm is kept on a frictionless horizontal surface at 20 degrees Celsius. The coefficient of linear expansion of copper is 2 into 10 power minus 5 Kelvin inverse. The Young's modulus is 1.2 into 10 power 11 Newton per meter square. Now the copper rod is heated to 100 degrees Celsius. We want to find the tension in the copper rod. Here the rod is kept on a frictionless horizontal surface and there are no fixed or rigid supports. As rod is not bounded, there will not be any compressive stress. Not bounded, so there will not be compressive stress. So if there is no stress, there will not be any tension. So no tension force. So the tension force in the copper rod will be 0. Hello students.